Okay, it is 10:30. We should get started. I'm Tony Tyson, and I'm going to present work from a lot of people in this very brief 10-minute overview of what's going on today. This is just sort of an introduction. We're going to hear from I'm really excited. We have an impressive lineup of people that are going to tell us about really exciting new things that have happened in just the last year in trying to deal with these satellite glints, flares, streaks, you name it. Not that the problem has been solved, but people are finally, after all this time, hard at work trying to do just that. So just remind you that we should be nice to each other. There are many contentious issues in this particular area, and I'm looking forward to debating them. We're all looking forward to debating them in a congenial way. So virtual participants should be muted when they're not speaking. So that's a voluntary thing. And Dan Polin is here in the front. Raise your hand so everybody can see you. And he's going to be moderating this and telling me to shut up or whatever is necessary to move on in a timely way. And he's going to be monitoring the Zoom chat as well as the Slack. So both he's going to be monitoring both of those.
And the microphones in this room are
And the microphones are up here, so you just have to speak loudly and you'll be part of the recording. And I assume we're recording. Yeah. Cool. All right. So this is an image that was taken on an 8-inch telescope. Imagine an 8-meter, what that would see. An 8-inch telescope with an f8 camera, 25-minute exposure to look at that comet, and you see what you see. And this is with the current, actually last year before last, current number of satellites. Multiply this times 30 or 40 for a mid-LSST survey, and then descale to half a minute, and you still have a big problem. This is sort of a message slide. So there are a lot of challenges in this business. The streaks themselves cause nasty things if they're bright enough to occur in our camera, and there'll be a little chat about that. There are, even if you attempt in your own science to mask the streaks, there are going to be residuals from that some people may want to worry about depending on your science case. In any case, all of this creates variability in glints, mostly because the streaks themselves aren't constant. They're constantly changing in brightness, and I'm going to show you a movie that was made by Forrest Fankhauser that shows that. This all causes things like bogus events and bogus alerts. And this even bleeds through to the static science. I'm going to have a slide on that. There are just beginning a bunch of people who are simulating their science in the presence of these problems, which is a lot of work, actually, because you have to do a full-scale forward simulation of all of the observing and then try to do your science case and analyzing those data with and without the satellite streaks and optimize. Meanwhile, industry is trying hard, many different companies actually are trying hard to minimize this problem by mitigating it by doing things to their satellites. And I'm going to talk a little tiny bit about that, and Meredith will also. So the one thing that I want to there's only one take-home message from this busy slide. And that is that if you take a look at the plot in the upper right, these are the number of filings. If you want to launch a satellite or even a single satellite, you have to file with the International Telecommunications Union. And they have to give you permission to do that. This is really basically optimizing the radio, but take a look. That's over. That's over 1 million paper. We call them paper satellites. Not all of that's going to happen, but many people in the know think that about half of that's going to happen. So we have a big problem. So I'm going to show you a movie from Forrest Fankhauser, one of our colleagues, undergraduate, who is now working at SpaceX, of a movie that he made. And it's basically on the left, what you see is the LSST focal plane. This was an arbitrarily chosen summer night, arbitrary time, arbitrary pointing from the data. And on the right, you're going to see the apparent brightness as a function of time in the focal plane as this movie progresses. And so okay, this is, you see a couple of them just briefly came in on the left-hand side, and then a bunch more come in on the right-hand side. And the take-home from this is that the brightness is not constant. So satellites are getting bigger. I'll describe why, but this is one of the smaller new satellites in the V2 family that Starlink has begun to launch. They can't fit the big one into their current rocket because Starship is not ready. So they've been launching these V2 minis, which is a small version. It's a mere 30 meters from end to end. The bigger ones will be over 50 meters in size. Why so large? Because of direct to cell, and I will be sending this to you. So it's not just Starlink, it's not just SpaceX. So there are a lot of companies getting on this bandwagon to be able to communicate directly to your cell phone from the satellite. To do that, you have to have a very narrow beam to focus on your cell phone. To get a very narrow beam, you need a very large phased array. Simple diffraction. And very large means very large satellite. And so on the far right, you see Amazon Kuiper's first attempt at launching. They've launched a few of these so far. They're getting bigger also. Take-home message, bigger, more satellites and much bigger satellites. There's a movie on the lower right-hand side, which we should be able to start. So this was a movie produced showing, and I'll show it again. This is looking sort of towards the sun. You can see Venus rising. I'll play it again. And you see these flares. These are easily visible. You can see these at night. This is the sunlight reflecting on the current generation of satellites. This is ASC Space Mobile's miniature version of their new fleet. This is a small version. The bigger ones are in production already. This particular one, which is called Blue Walker 3, is first magnitude. The other ones are going to be around -2, and their constellation will be that bright. Luckily, there won't be an infinite number of them, and so there'll be a countable number of them, and we could probably avoid exposing them near the focal plane. That's not true of most satellites, however. So here's what happens to the camera if you do any of this, and this comes from laboratory measurements. The ideal detector is shown on the left, where there are no camera effects. You still must deal with the streak. The middle one, you can see what happens if you in the laboratory illuminate it with a streak. You can see the crosstalk, this parallel tracks. That's the headache. And some of you, depending on your science, may worry about that. And on the right is Blue Walker 3. It saturates the detector. Alerts are most affected by this. Only a small fraction of the pixels will be affected. Depending on your science, you may or may not care about this. In the coads, there are effects that lead through to, as I mentioned, to the variance planes. Difference images are infected by this, causing focus alerts. You're going to hear more about that from Meredith. Even the catalogs, it goes through all the way to the catalogs, bits of the above, again, depending on your satellites. At the moment, there are over 40,000 tumbling debris with the current number of satellites. And we're going to hear in the next talk about what that implies. Okay, so that's the introduction. We're going to hear next about this debris in low Earth orbit from Adam Snyder, differencing images and masking but from Meredith, streak detection and AI from Jack, and regulatory considerations from Ashley. And then we're going to reserve 20 minutes at the end for a general discussion. After each one of these talks, there's going to be a short few-minute question and answer period. Okay, so I'm going to unshare. You don't need this. No.
I think it's all working out pretty well. I'm Adam Snyder. I work at UC Davis with Tyson. There's been a lot of talk about satellites. I'd like to talk a little bit about a different effect caused by low Earth orbit debris that is distributed in a power log number, log size power law distribution. So this is debris that can cause specular reflection. We call them glints. That will then be observed by the LSSD camera. In particular, low Earth orbit debris that is less than 10 centimeter diameter is troubling because the glints that they cause will be indistinguishable from astrophysical phenomena. They are not tracked like debris that is larger. So we wanted to, this is a brief study on what we might expect from this glints that is caused by debris that is in this range of sizes. First, we calculated the apparent brightness for two cases, a 1 centimeter and a 10 centimeter radius debris. We had to make a number of simplifying assumptions in order to do this. So an albedo of 0.1, 500 kilometer orbital height observed at 60-degree angle from zenith. In terms of the reflective properties, we assumed a diffuse reflection over one hemisphere and a glint time of 1 millisecond. So I was able to use the Rubin simulation tools that exist currently to determine the throughput of the expected throughput of the camera. This gives a sun AV magnitude and G band of -26.5. From this, it could then calculate total flux one would expect the glint, and then equate that to a magnitude. So for the smaller radius debris, this is an important distinction. There's two magnitudes that we kind of refer to. It is a 16.6 magnitude object observed for 1 millisecond, but of course, we're integrating for 30 seconds. So you have to convert to what the equivalent bright object would be. So for this 1 centimeter debris, it is a 27.7 magnitude object. So if you were to perform photometry on this in the LSSD survey, this is what you would equate it to. For the larger case, you get again 11.6 magnitude object if it was observed for 1 millisecond, and equivalent 22.7 magnitude object as observed by LSSD cam. In G band, we have a 24.4 limiting magnitude. So given our assumptions, we believe a 1 centimeter debris, the object causing a glint would not be detected, so people lower detection threshold. But for the simple case that we modeled here, a 10 centimeter glint would be. But of course, there's two other effects that we have to consider. The first and probably most important is the effect of defocus. Unlike stars, which are effectively at infinity, the debris is quite closer and thus will appear out of focus. And you need to consider the effect this will have on the observed PSF or observed surface brightness profile. So basically what we need to do is convolve the profile of the debris, which is effectively just a little dot with the atmosphere, and then this last important factors the defocus kernel, which is just basically what the pupil of your telescope looks like, projected, the angular size of it, given the distance from the telescope to the debris. And this was done using this software that I wrote. I included the link to GitHub for anyone who's interested. So here's what we get. We have the stationary glint. So this is what it would look like. This is a 10 centimeter radius object. This is what it would look like if it was observed and you tracked it. The moving glint, you can see it's a little bit blurred out. It doesn't get blurred that much because it's very quick. And then the equivalent flux star PSF. So when we previously calculated the magnitude, this is the equivalent PSF size. But as you can see, when it's out of focus, that flux is spread out over a larger region. And I should mention the atmosphere was 0.73 arc seconds, which is sort of the median seen. And this is really kind of the point that we were trying to make when considering the defocus, is that when the object is now focused, the peak brightness is substantially decreased. In this case, it was lowered by almost a factor of 6 compared to the star PSF as the equivalent flux. So briefly, the process for transient detection is to convolve the image, convolve with the image PSF, and then set a detection threshold as a multiple of the image noise. And because of the change in the peak brightness, we expect that the signal of the noise will be substantially decreased and will reduce the number of detections for even the 10 centimeter object. And given this consideration, we expect that for the previously outlined assumptions of reflectivity, that 10 centimeter radius debris causing a glint would be at the very edge of the detection threshold. Unfortunately, there are some additional considerations. Of course, we made several simplifying assumptions, in particular regarding the reflectivity. So centimeter scale debris can have albedo approaching 1. That's 10 times larger than what we assumed. There's of course a distribution of the orbital heights of the debris. Objects that are at higher orbital heights, they move more slowly and they are more in focus, but of course they're also fainter since they're further away. Using the model that I previously outlined, we calculated a decrease in the peak brightness of a factor of 1.4 for a 1,000 kilometer orbital debris. This means it was actually dimmer, so that's good news. We expect the factors that make it fainter to outweigh anything that might make it have a larger peak brightness. One concern is that we assumed a uniformly diffuse model, but this was incorrect for mirror-like surfaces. For example, shards of multi-layer insulation. It's expected that there is a minimum of the LSSC wavelengths for the usual space material. So maybe this isn't something to be too concerned of, but it's something that needs to be considered. And then, of course, regarding the capabilities of detection, there was a very nice figure of the transient factory showing glints that were appearing, and they have this beading structure, which is it's pretty spatially repeating pattern that may actually aid in identification when developing algorithms to detect glinting debris. We have a short article. I included the link here that goes into a little bit more in-depth discussion on different effects, other considerations, things like modeling the reflective properties. So I think that's all I really wanted to talk about. And just to summarize, we've heard satellite streak identification and masking has been sort of our main concern. We now also know that we may have to look more deeply into how glints from debris are detected and how these might be removed from transient science. And then finally, I just wanted to sort of preview another effect is objects that flare and have a very large variation in surface brightness. So for example, this image on the right that shows a satellite that is flaring becomes substantially brighter and its profile is changing. So this may require new detection methodologies beyond the usual or the current street identification. And that's it. I think I have some time for questions.
Yeah, we have time for a few minutes for questions. First of all, anyone here in the room?
Have you, thank you for this great talk. Have you looked at all into the color from the space debris glints and whether there's any way to help discriminate astrophysical sources from sunlight bounced off of various bits of debris? Is there any diagnostic there?
I mean, obviously, the first, serial order is that it would have the same, spectral distribution as the sun, since that's what's reflecting.
Right.
Then, of course, that depends on the material, what's absorbed. I don't think we've really looked in depth on, absorptive properties of materials.
We have some laboratory measurements of MLI, and for complicated physics reasons, happily, it has a minimum in the optical, maximum as you go red. But by about a magnitude, so it's not a solution. It's not a general solution to this problem.
Yeah, some of the debris, there's some question. It'd be very hard to know exactly, what is controlling a lot of the debris. It might be at different parts of different spacecrafts. Let's see. Yes.
Is the debris concentrated in a certain area of the sky, and then in that area, is it kind of like uniformly distributed? We know sort of like the count versus the size, and it is. I would hazard a guess that it's mostly uniformly distributed. I'm not sure.
It's everywhere. If you look at the upper right hand part of this little plot, they look at different parts of the sky, and it's pretty much the same everywhere. This is radar data, recent data.
And it has a distribution in orbital heights as well.
Yeah.
500, up to 1,000. Yes.
Yes, speaking on behalf of Alerce Broker, we have been worried about these glints because we cannot distinguish them from real transients, especially with the very small unit stamp that the SFT will have. It's 6 seconds versus 13 CDF. So you will not be able to see the consecutive detections.
It depends on the tumble rate. Also,
yes,
how quickly it glints.
So my question is, if you have tried to study this rate, so what will be the distribution between separations to understand what should be because we will rely on the 65 level. We will not be able to tell from another.
That's a good question. The project is making adjustments to this. in collaboration with the agencies. And I can assure you that they'll be larger than a few arc seconds available. We do not alert on long streaks for good reasons, but certainly you should be able to see immediately something larger than 6 arc seconds, and then go back and get forced photometry on even larger areas of the sky.
And also, like, the simulation is not at which distance does it become like indistinguishable from a star? Yes.
Oh, I had a good graph that I wasn't able to include that sort of shows its brightness compared to sort of like, you know, as it gets further away, it becomes more in focus. And then of course it becomes dimmer. I was not able to include that, so I don't know it off the top of my head. For the most part, it never really, you know, fully becomes in focus. I think at that point it would be so dim you would not be so concerned about it. It would always, they always almost appear, you know, with this donut shape. That's the telescope people.
All right, we are out of time for questions. I think Meredith is up next.
Thanks. Yeah, Meredith.
Hello, everybody. Let me get my screen share up.
The press.
And hopefully that, no, I don't want to rate Keynote. I am not enjoying it any more or less than usual. Can you all hear and see me all right?
Yep.
Wonderful. Thank you for the invitation to join this session virtually. Hope you're all enjoying those of you who are there in person, hope you're enjoying your time of Slack. So I'm going to speak a little bit to the plans that Science Pipelines has for dealing with streaks and glints that are kind of still being developed, but we do have some updates since I presented on this last year. But I did want to open with just a couple of kind of big picture, where are we now? Tony touched on this, but actually the plot that he showed was just updated on Friday. So this plot here is one that the European Space Agency makes. They do an entire space environment report every year, and they dropped a new one on Friday, and it's increasingly crowded is the short takeaway. So the little dashed line I put here is where the y-axis stopped last year. And as you can see, 2023 was yet another record-breaking year in amount of things launched into low Earth orbit. And the SpaceX Starlink is the bulk of these, but there are many more players jumping in the bit to join the fun. And so as of now, there are over 6,700 SpaceX Starlinks that have launched. But last year when I gave a talk, it was only 4,400. So welcome to your new orbital space environment, everybody. Most of the active satellites are commercial, like the Starlinks, and in low Earth orbit. And as we all know, they reflect sunlight. We're not going to go into the details of all of this, because I feel like most of you have sat through a talk like this at some point, kind of giving an overview of the problem. This is not news. But Rubin operations is going to coincide with this new era in low Earth orbit, kind of like it or not. And there's probably going to be between 50 and 100,000 active low Earth orbit satellites during this time period, so we need to be ready. A few things that are new that Tony also hinted at in his nice little introduction, one of which is that direct to cell, these really big satellites that talk straight to your cell phones, everyone wants them, right? Like all of the cell phone companies are like, wouldn't it be cool if you could just like pick up your phone and talk to a satellite? Like everyone wants that, right? You know, I can appreciate that. But what it means is that there's going to be really big satellites lower to make that like physically possible. And SpaceX has already started launching some of their Starlinks that will serve this purpose, and they are inherently brighter because they're bigger and they're closer, but they are in a lower orbit, so they don't linger as long in the sky on any given point. So that offsets the increased inherent brightness a little bit, but not as much as we would like, is the short of it there. Happy to talk more about that later, or Tony can answer questions as well on that later. In addition, the one of the peak space sustainability things that operators sometimes will advertise is that they design their satellites to burn up in the atmosphere on a time scale of about 5 years, which sounds great when you say it fast, but what that means is that we are now starting to deposit unprecedented amounts of aluminum and whatever else these things are made out of into Earth's upper atmosphere. So we are doing a real-time chemistry experiment with the Earth's atmosphere, and we don't really know what that is going to yield. But if history is any indicator, it's probably not going to be a completely neutral zero effect. And so people are starting to study this, but it's not well understood yet. There was a solar storm a couple months ago. Perhaps you got to see the aurora. I was here in like urban Seattle and went up to my roof deck and saw an amazing aurora show. Much to my surprise and delight, woke up my kid, dragged her up there. But when that happens, satellites have a harder time orbiting because they have more stuff to orbit through, so they start to lose altitude. And all of the couple of operators who shared information about this time period were like, our hardware all survived, we were prepared, like everything is fine, do not worry about it. Because previously when there'd been a little solar storm, a few of them had like completely deorbited unexpectedly. But this time they were all happy they survived. But the kind of part that it wasn't talked about was that actually all of the ones that had maneuverable capabilities were doing what I'm going to use as an analogy, like the duck on the surface of the water, right? Is just kind of happily going along, but underneath they're going like this. They were firing their thrusters for all they were worth. They were just, trying to not lose altitude. And while that's fine, if a few satellites are doing that, every single satellite that could do that was doing that. And we didn't have enough real-time updates on their positions to do collision analyses. So that is a potential issue. Again, not going to go into that in detail because apparently I've already used half my time already. So as Adam already said, the biggest consideration that we have from small debris is probably not going to be from the small debris chunks actually showing up as sources most of the time. But instead, there's going to be kind of an overall increased diffuse sky background brightness that results from a huge cloud of crap that is ever increasing and very small. And that is going to change over the course of the 10-year survey. So that is something that we need to keep an eye on as time goes on. And then in addition, I want to just briefly advertise that the IAU Center for the Protection of the Dark and Quiet Sky from Satellite Constellation Interference, or CPS for short, I co-lead the SatHub group at that center, and we are continuing observation campaigns, developing data sharing tools like this Sat Checker tool that will tell you when a satellite's going to pass over your location. And we are communicating with industry partners. And if this is the kind of work that you're interested in, please do join us. Okay, so with that context, I want to give you a little bit about what to expect during Rubin operations in terms of there's going to be stuff in your data. What are we going to do about it to help prepare people to hopefully be able to distinguish astrophysics from junk, right? So here's a very basic schematic of our difference imaging system, right? You got a new science image, you have a template reference image that's deeper, it's been co-added, you do some subtraction, you get some sources, you find the sources, you send some alerts, everyone's happy. It all happens very fast, nothing falls over, perfect. However, reality, there will be some satellite signatures in some of the science images. Some of them will be like linear streaks, some of them will be weird glints. They will show up in the difference image because that is how difference imaging works. They will also often be detected as sources if they are bright enough. So what are we going to do about that? What I'm working on right now is two different ways to approach this. One is detecting the streaks and adding a pixel mask to the area where the streak is, so that if you are going to then go and look at difference imaging sources that are in that region, you will know that maybe you should take a bigger picture, a more detailed look, get a better context for those sources because maybe they're actually part of a streak. In addition, detecting glints, like these little stripes of bright things that, or trails of bright things that maybe aren't all part of a streak. I'm detecting those as well and sending those sources as well to a different catalog than the main difference imaging catalog. So just a quick look at streak detection and masking as it currently stands. Just want to be really clear up front, neither of these processes or anything that I'm talking about is actually throwing away any pixel data. When we say masking, we don't mean like erasing with some kind of horrible like whiteout or whiteboard eraser situation, right? We're keeping the pixel data, it's still there. This is all about trying to figure out what goes into what difference imaging source catalog and what doesn't. So we have a kernel-based Huff transform algorithm that detects linear features on the difference images. And we look in particular, we look at the detected mask plane. So I have an example down here of a difference image, and then the detected mask plane where we run our detection algorithm and it finds things. You can see there's a streak, spoiler. We also, because it's a difference image, we also find some negative detections, and there's a bright thing over here that's making a mess, but that's just life. And then we have other pixel flag information, like for example, there's some regions with no data, because again, that's life. This is some HSC precursor data that I ran this example on. And then usually the streak detection software will find the streak and add a streak mask in the location of the streak. And you can move on with your analysis, knowing that the sources there are associated with the streak. We're currently in the process of testing the performance on real HSC and DCAM data. And of course, I have picked a representative example, which means this one looks great and some of the ones that we have don't look great. So that's a work in progress. Here's an example of kind of an interesting one where you can see there's a faint streak, right? But it didn't really fully meet the detection threshold. So then the streak mask only gets the bright one, or I don't know if it's brighter, but it's less diffuse, I'll say, and it doesn't get the other one. And is that desired? Maybe detecting glints will find this one instead. Stay tuned. We have a prototype glint detection algorithm as well that Ari Heinze has kindly coded up. And he successfully ran it on some Atlas difference image data and found these glint trains. It identifies bright difference imaging sources and then finds nearby neighbors that are evenly spaced. And then it is able to flag those as likely glint trails. So the idea here is to use a combination of the streak finder and the glint finder and make catalogs of difference imaging sources that aren't science. And so those will be in separate catalogs. And then all the things that aren't potentially affected by that will be in like the real difference imaging source catalog that will generate alerts, etc. A few other considerations as we move forward in this work is that the streak masking algorithm is also used to reject some artifacts during co-addition. And we might be able to improve that by using the full difference image streak detecting workflow, and then go back and use that information to help improve our co-addition. We haven't gotten that put together yet. The goal here is to have no streak or glint identified DIA sources in the final DIA source catalog or in our alerts. At the moment, there is no streak mask information that exists at all prior to difference imaging, since this runs after difference imaging. So, but there are, like I said, opportunities to potentially kind of connect that back to earlier in the pipeline when we're building our template coads and things like that. Happy to talk more about this if folks have questions. I want to emphasize that the total impact of science depends on a lot of things that we don't have control over. So the way that I like to frame this is to think about quantifying and controlling the variables that we can for Rubin and LSST data. And so that is understanding the camera's response, which folks in the room and on the call have been working on, and then and making sure that the image processing pipelines are handling the weird things that we find in the way that we want, and that is what I'm working on. However, we don't have direct control over the number of satellites, their orbits, or how bright they are. And so that is why I would point you to these excellent organizations. Compass is one of the AAS committees that is doing really great work in advocacy and policy to try to get this to be less of a big problem. And then the IAU CPS that I mentioned earlier is also doing a lot of work on all of these different fronts, broader than just like the technical image processing area. Okay, here's my last slide. As kind of a takeaway here is that there are a few different angles for approaching this problem. Again, back on like the algorithmic data processing side of things. So if the satellite population is really large, or some of them are really bright, we can adjust the scheduler to where we point the telescope, right? We had a proof of concept showing this is feasible, but it does require accurate and precise satellite path predictions, and it also sacrifices some amount of time, right? Because it adds time to the survey. Great news. A group of us just were awarded a new NSF grant to work on developing tools that will enable this. So we are going to be building a field of view path prediction tool that will use some of the highest accuracy satellite position data available, and it will enable this kind of dodging or avoidance if we do wind up needing it during Rubin operations. We're also going to be able to retroactively measure the rate of false alerts or false data sources due to these kind of signatures once we have this tool fully built out. And we also want to be able to quantify how the satellite population is affecting our ability to do different kinds of science. And in particular, this grant is going to focus on solar system object detection and characterization, because my colleague Siegfried, who I think is here, is also involved in that work. So I know I've gone a minute over. I apologize. Thank you for your flexibility. Please do reach out to me if you have specific concerns about how these things may affect your science, because I want to hear from you. Thank you so much.
We have a bit of time for questions. Anybody, first of all, starting in the room? Okay.
So maybe this question also for Adam, but can you say generally, what fractions of night is this an issue, a major issue, and can it be avoided by pointing? Like Adam, for example, you mentioned, I think your study was 60 degrees from zenith, et cetera. So
I think you'd expect more of them, earlier, later in the night, and closer to the horizon,
Yeah.
because it's reflecting the sunlight.
Yeah.
So there's a lot near twilight.
Yeah.
Morning or evening twilight, but there surprisingly are quite a number at midnight, and we're trying to wrap our minds around what's going on there.
Okay.
Could be something funny with the solar panels.
okay. Yeah, I guess my question is there a part of the night that we don't have to worry about it? Or is it
Really,
always
no,
a bit of an
I'm
issue?
afraid. I mean, it's minimized at midnight, and maybe depending on your science, you don't worry about it, but maybe you do. So, as Meredith said, it really depends on your science base.
Yeah, if you need to
Andy?
do a bunch of observations close to twilight, you're going to have the worst time in this regard. And we do have a bit of an advantage in that the majority of the wide, fast, deep survey is not pointing near the horizon and is not happening during twilight. So that is like helping us overall, because that's when we see the most of these that are brightest, but they are everywhere. And there's no escaping them. Even in the middle of the night in winter, you're going to get a few.
We're going to hear more about that in chat coming up next. Andy, did you have a question?
Yeah, you talked a lot about using precursor data sets, whether it's HSD or VanderLey. I was wondering, are you doing anything on simulating what these streets might look like and modeling them so that you can inject them into the data stream?
Yeah, that's a
There's
great
a lot of-
question. Dan might be able to speak to that. Actually, you've done some work. We haven't injected it yet, but we do have an understanding of what different brightnesses do to the camera. Do you want to speak to that, Dan?
Oh, so just at UC Davis, we have a CCD from both vendors, and we image street masks onto the CCD to simulate how it would actually impact the CCD. So we do have some measures of that.
And do you tie that to the expected population?
Yes, that's the next step.
We tie that to magnitudes, and then we know the distribution of magnitudes that currently exist and are planned.
What hasn't been done by the community yet is to fully simulate your science case using this information. That's the next step to us. Questions? Oh, sorry. Yes, question here in the room.
No, yes, I mean, I was looking at the Carpo Pelotón paper with the distribution of the semi-major axis and duration of the flash. And basically, most of them are higher than 500 kilometers, so some are even in geostationary orbit. So I think this question of the distance and this will also explain why sometimes you see them in the middle of the night. It's worrying.
Yes. It's worrying. Okay.
So we have one question on Slack we might have time for.
Yeah.
Do we know yet what sort of effect the inclination of the satellite will have on the street?
Inclination is going to give a streak at that inclination.
Yeah.
And we see streaks from polar orbiting satellites, a lot of them. You saw that in that image I showed. And we see streaks from inclinations as small as 30 degrees. So all of these inclinations are going to be populated by these various different companies. They have to in order to have coverage. So the inclination distribution is going to be uniform eventually.
And basically any inclination will cross the seeing of the LSST is the big thing that we're.
Yeah, we'll see them no matter whether they're polar orbiters or
Yeah.
not. So
Yeah, the brightness that shows up to us as well is also a function of the attitude of the satellite. And this is something that we don't always have good information on exactly how it's oriented, which part is like glinting towards us at any given moment. But my understanding is that the satellite operators often do have access to that information. And so that's one avenue we're pursuing, is trying to coordinate with them through the CPS Sat Hub to better understand what information we might be able to have for the Rubin site, for example, of, is it possible to make sure that the majority of the satellites are oriented in such a way that we are less likely to get really bright flares at our location. But that is very early discussions, so nothing concrete yet.
I think
we're out of time. Thank you very much, everybody. So Jack, are you ready to go?
Yes, I am. Let me just get my screen sharing. Okay. Can everyone see that now? Hello? Can you hear me all right? Okay, cool.
Yeah.
Just making sure. Great. Awesome. Okay. So hello, everyone. My name is Jack Patterson. I'm a first-year PhD student from the University of Canterbury. And today I'll be talking about some of the preliminary work we've been doing to build up a robust artificial satellite detection pipeline for the Class C survey, which is CFHT, and I'll talk about that in a little minute. And talk about some of the challenges both this survey and LSST are and will experience based on what we're seeing in the data so far. So I'm supervised by Michelle Bannister and James Atlas, and this work would not be possible without all of the amazing Class C survey collaborators that you can see on the bottom of that slide there. So first, just a super quick primer on the Class C survey. This is a large program on the Canada-France-Hawaii telescope that is looking at Kuiper belt objects, trans-Neptunian objects, and extreme TNOs in the cold classical belt's mid-plane. Some of the primary goals of this are to measure the size frequency distribution of classical TNOs, to test various formation mechanisms, and to test emplacement models for some distant TNOs. But the bottom line is that it's a solar system survey, and we're doing difference imaging on the same area of sky repeatedly throughout the night for object discovery and tracking. So we're using MegaCam. It's a wide field imager, and this is a 4-meter class telescope. So just a very brief comparison between this and main survey of LST. Obviously, the main differences being Rubin is an 8.4 meter with a 3.5 square degree field of view, so wider. And that means to get similar results, need significantly more integration time on CFHT naturally. However, the single exposure depth in R-band, which is what we're using for discovery in Class C, is similar. And both sites have similar pixel scales and excellent seeing. And with such wide fields of view, we do already see many streaks. So as I mentioned, because we're performing discovery of moving solar system objects, we're using difference imaging, which means single exposures are important. So however, as Tony mentioned earlier, there are multiple other situations, depending on your science, that will also see the impact of streaks in LSST, such as those around twilight, and especially for alerts, just to name a couple. So to illustrate the problem, I'm just going to bring up a selection of streak cutouts. So this first one is a pretty standard, your standard thin line of relatively constant brightness. However, these aren't the only ones around, and just note that these aren't actually difference images, just for illustration. So there are also much fainter streaks. There are much brighter ones that can vary in width along their length. there are streaks also with one-off discontinuities in the middle there. And there are streaks with more regular changes in brightness, depending on the attitude and the rotation. This one also happens to have 2 streaks crossing over one another. And then there are some larger ones with constant brightness, but there are also these huge brightness flares that we often see. So not only are these potentially obscuring the targets directly, but you can see an outer region of the CCD area kind of surrounding the brightest part is actually secondarily affected by the peak brightness there in the middle. And there's just another one of constant brightness. But the important thing to note is that this variety is not just a tiny fraction of the edge cases. We're seeing a significant number of these kind of non-standard brightness streaks in the Class C data, and expect, you know, a similar variety in LSST, especially as more satellites are launched and we get more debris in the sky. So from this, can we properly detect and mask these is the question. So, well, first we started by creating a data set of these streaks. So MegaCam has 40 CCDs per frame, and they're around 2000 by 4000 pixels in resolution. And so far we have just over 3000 subframes manually annotated with streak bounding polygons, and soon to be more, which we're using to test a variety of different approaches. And in case you're wondering, this data set is planned to be publicly available at some point. I don't have a timeline on that yet, though. So using this data set, a software framework has been developed to assess the effectiveness of essentially any detection approach you can throw at it. The idea was to allow for easy, uniform assessment of multiple approaches with the same suite of metrics to compare methods as best as possible. And so far, 11 methods have been tested, although more are planned, but I'll just go through some of the initial results here. So we're just going to consider one of the main metrics here that we are looking at, which is the Dyson coefficient. All this is a measure of the overlap between your ground truth labeled data and your predicted values per method. It just ranges between 0 and 1, with 1 being the ideal case of perfect overlap. And so far, we've tested 2 groups of methods. Firstly, those that rely on classical computer vision techniques like half-full radon transforms, like Meredith mentioned before. And secondly, we've also tested a variety of deep learning-based techniques, and some of which also integrate aspects of the classical techniques into their architecture. So each of these methods have only had a small amount of fine-tuning for this data set, as we wanted to get a performance baseline before extensively tweaking each approach. But in bold there, you can see the best performing method only has a Dyson coefficient of around 0.5, the remaining approaches kind of falling quite a bit lower than that. So what's the reason for that? Well, the problem is that while most of these methods can perform very well on standard constant brightness or relatively constant brightness streaks, like the first one that I showed earlier, the other types of streaks, especially those with time varying brightness and shape, result in much poorer performance across the board. So just here are those images again, just with outputs from various models showing a small sample of these issues. So overall, kind of taking into account all of these features is something that we're kind of still actively working on and really would like to solve, but you know, it's still a work in progress. So yeah, so however, as Tony said at the start, so even when accounting for these, there are challenges in actually applying the masks that you get out. So we need to consider streak masking residuals, and non-linear crosstalk for LSST in particular. And we really want to carefully weigh the impact of false positives and negatives, because if you're subtracting a phantom streak, that's going to really impact your science data. There's also the fact that even if you have a correct detection, if it is slightly off, either in angle or in thickness, your residuals are actually going to be quite significant. So one of the things that we've been thinking about in our group at the University of Canterbury is, can we model the full trail PSF of the entire streak so that we can perform subtraction? This is a big challenge, especially with the hugely variable streaks, but it could provide some great benefits to doing subtraction for both Class C and LSST. So lastly, as we've seen from everyone before me, we are expecting a huge number of satellites. So over 6,000 Starlink already up. They're the big player, but they're not the only one in town. There are more coming up. We're expecting at least over 100,000 LEOs, and there are many, many more on paper within Rubin's lifetime. And we are already seeing the increase year on year in the Class C data. So on the right there's just a graph of Class C exposures that have been identified by humans to actually contain satellite streaks so far. So to conclude, while a variety of streak detection and localization methods can perform really well on your kind of standard run-of-the-mill streaks, there is still a lot of work to be done to correctly handle time-varying morphology and especially glints and flares. In the near future, we plan to test many more detection methods and fine-tune the most promising approaches for our pipeline in particular. But while this testing has been performed on Class C's wide-field images, these images are also serving as a test bed for the same problems with detecting these streaks in LSST. And as I mentioned, the dataset and framework are planned to be open source. Don't have a date on that yet, but we'll make a post about that in the near future. And looking forward, there are still improvements to be made for both detection and subtraction in general. There are many great people working on this. But the plan is to take what we can learn from Class C and apply it to LSST when Rubin comes online. And with that said, that's it from me. I'd like to give a big thank you to the session chairs and everyone that's attended today, and happy to take any questions.
I'm sure we have some questions. One question from the audience first. We have a couple of minutes for questions. No questions here. Okay, online, I think we have a question. Question online?
I don't see that we have one.
Okay. Any questions from the room again? Okay, good.
I'm curious. So some of the things, the misidentifications, Jack, they seem to be maybe associated with stellar diffraction spikes. Is there a way of running this after kind of those are masked? Would that, how much would that help in this process?
Yeah. So that definitely helps. Doing it after masking can reduce a significant number of those, not necessarily entirely, but those aren't kind of the main issues we're seeing. It's more to do with the flares and the variations in brightness. It was just one kind of smaller example. Those are far less common, I would say.
Question.
So Siegfried, you have a question?
Yeah, thanks. And thanks, Jack, for the excellent talk. First, a comment. When you're done, and all of this is published, please contact us at CPS. We'd love to have your code be made available for other folks as well. And the second is a question. So you showed like the coefficients for not only for the method of your choice, but also for machine learning, and they did really, really poorly. Do you have intuition why those machine learning techniques were doing basically one order of magnitude lower than what we would expect or what we would want?
Yeah, so there are a couple of reasons there. One is that we're kind of pretty cautious of overfitting on the existing data set we have. We only have a relatively small number of labels for training. So there is that kind of consideration. Also, the fact that a lot of these approaches, while they integrate parts from classical techniques like adding in Huff transforms to some of their CNN blocks, like in the middle, they weren't really designed for a lot of the style of data in these astronomical images. So they have a lot of trouble picking up, well, I guess discarding a lot of the information that's not relevant. So another thing that we want to try is, well, we've already tried some, but another thing that we want to try is more image segmentation based approaches with more training data, and see if we can get some much better results, especially by fine-tuning the network architectures themselves to actually be better suited to this problem.
Thank you.
Okay. So no more questions. I think we're off to Ashley. View of the policy issues.
Great. I think I have my screen shared. Can you hear me?
Yes. Yeah.
Fantastic. Well, thanks so much to the organizers for the invitation to give a quick update. I'm sorry I can't be there, but appreciate getting to hear about all the great work that's going on. I think it's really important, especially for the satellite operators, to see how much detailed work and study is going on by astronomers to find ways to mitigate on our end, as well as the things that we're encouraging them to do. So today I wanted to give you just a quick update, both internationally, so some work going on at the United Nations and the ITU, also some things domestically, and then just finish up with a couple comments on some funding and some things that are happening at NSF. So I wanted to start with the ITU. I was glad that Tony mentioned the paper filings. You know, the ITU, generally people think about the radio spectrum, so how does it relate to Rubin? But it is very important because what's happening in the ITU impacts the optical, because this is kind of what's generating this huge rise, kind of the mission there, and every satellite is going to need some kind of radio comms. So wanted to highlight, most of you probably are aware of this, but the place where you'll actually find the rules and you'll see details about satellite coordination and what frequencies they're allowed to transmit in is the International Radio Regulations. This is updated every 4 years. And so one big update we've had since I was able to speak to the workshop last year is that there was actually the World Radio Communication Conference in Dubai in November and December, and that was preceded by the Radio Communication Assembly. So one really important thing that happened, there was actually a lot of discussion about satellite constellations at both the Radio Communication Assembly and the World Radio Conference. So one thing for radio that took place that was interesting, and this might be something I believe the IUCPS is kind of working on in parallel, is they actually approved establishing a database for radio quiet zones around the world so that operators would know where people are really focused and, you know, putting a lot of energy from a national regulatory perspective to try to protect their ground-based radio assets. So this was approved by the RA, and then Study Group 7 in April actually implemented with sort of a template of what information would be shared. And so this is the kind of thing that I think it's great that we have the IUCPS that can also start to pull together, you know, impacted optical observatories. And it was great to hear that talk from, you know, how CFHT is being impacted, because we very much jumped in and started focusing on impacts to Rubin as kind of a limiting case. But I think at this point, we really do need to start to understand the nuances of how different kinds of telescopes and cadences are going to be affected by satellites. At the World Radio Conference itself, two things I wanted to highlight that are of relevance. There's actually an agenda item related to astronomy for the first time in many, many years. It is focused on the radio impacts from non-geostationary satellite orbit systems, but this means that there's a lot of conversations happening right now about the impacts that these NGSO systems will have on astronomy. The other thing that was really important is there was a resolution passed on space sustainability at the ITU. And so this is interesting because oftentimes the ITU has kind of punted this topic, but this was a huge priority for a number of administrations. And so they did actually pass this resolution looking at sustainable use of radio frequency spectrum, but starting to look at all kinds of things. If you look at what they instruct the study groups to study, it includes guidance on safe and efficient deorbit and disposal strategies. So not just the RF spectrum. So that was really interesting to see that. And then they also have a number of activities that they're asking to work towards, including the collaboration and exchange of information with COPUS, the Committee on the Peaceful Uses of Outer Space. So this is where traditionally we've seen more of a focus on the optical impacts. So I wanted to just highlight one really exciting kind of bit of progress at UN COPUS is there'd been an effort for a number of years to have sort of a consistent place to discuss dark and quiet skies and to start to think about what are best practices that we can all share on an international basis. So the Scientific and Technical Subcommittee early in the spring had recommended a 5-year agenda item on dark and quiet skies. And this summer, the full committee just agreed to that. So that's really exciting that we're going to know February this coming year, and for 4 years following that, there will be a dedicated agenda item where different nations can bring together their thoughts on recommended best practices to mitigate the impact of satellite constellations on astronomy. So I wanted to highlight this because, you know, there's lots of opportunities to contribute information, you know, depending if you are from the US, you know, through the US administration or through other administrations. And there's also a good opportunity to contribute technical papers as well. In conjunction with that, there is also established an informal group of friends for dark and quiet skies. It's going to be kind of meeting in parallel and helping to prepare things for the subcommittee. And so if folks are interested, again, I would note that within the US, there was a Federal Register notice for people who were interested to join a discussion group. The deadline for that is passed, but if you do have interest in staying, you know, abreast of what's happening and contributing, you can reach out to Tony Tyson, who is participating on behalf of Rubin. You can also reach out to me. I'll be working with the State Department to try to collate, you know, stakeholder feedback so that what we bring from the US back to the group of friends and into the committee and the subcommittee fully reflects all of this great work. Some of the simulations that are being done, I was really heartened to hear how much work is being done looking at simulations of science impact and really digging into that. So I think that would be a great example of, for example, a technical presentation that could be given at COPUS. I wanted to highlight here's examples over the past couple of years of technical presentations given from just the United States on satellite constellations, but this is really just to give you a flavor that there's opportunities for these kinds of technical presentations, which are short, kind of 5 to 10 minute presentations, but it does give an opportunity to share what is happening more broadly. And so in addition to that dedicated agenda item, this is always an opportunity. And then also just wanted to kind of note that the US has made very strong statements over the past couple of years about its support for finding ways to mitigate the impact on astronomy. So this is something that, you know, through that group of friends, and reaching out will, you know, hopefully continue to find a strong voice there that will be able to speak towards, and this leads towards eventually policies. Because at this point, there's no structure like the ITU to actually set regulation, but this is kind of a place where if we can establish, for example, you know, a resolution that sets, here are the best practices that we all agree to worldwide, that would be a really good start. Now, I want to just transition for a couple minutes into some things that are happening domestically. So the direct to cell was mentioned quite a few times. There was a rulemaking from the FCC. NSF, we put in a rather lengthy white paper on the record, primarily looking at the impact that this might have on radio astronomy, but we did mention the impacts that it could have on optical and infrared from these large satellites. So this is one thing that we pointed people to, is that, you know, we encourage the operators to follow the best practice guidance that is set by the IAU-CPS and other work that's done. So I wanted to highlight this, that's one thing NSF, we keep saying, hey, the best practice guidance that's recommended by the IAU-CPS, and that comes from you, from the community. It comes from your studies, work that, you know, you come to, hey, 7th magnitude, maybe 6.5 magnitude is going to be good enough. You know, and continuing to ask the question so we really understand that what we're recommending is not overprotecting, but it's exactly what we need to get the science done. So this is going to be really important. We're watching this closely, how the supplemental coverage and the direct to cell develop. So currently there is a rulemaking that permits operators, but no licenses have been given yet. to do this. There is a temporary authorization to SpaceX, and we're doing some tests in the radio, but I think we'll start to see more of that rolling out in the next year. And so that's where it's going to be really important to coordinate it and to work with these companies. So this leads me to the coordination requirements that the FCC has put in place, and it's great. The US has actually been kind of a leader in this space. These are a couple of slides from the presentation at COPUS by the FCC. And one thing I wanted to highlight is the reason the FCC put this in their authorizations was they considered the public interest as kind of part of their overall analysis. So we were really happy to see that they added this into, I believe, 5 or 6 of the authorizations now, a requirement to coordinate on the optical issues. So this I had spoken about last year, the requirement in the Amazon Kuiper constellation. We have, as I mentioned, about 6 now. And this is where when NSF goes to coordinate, we really look to kind of push the company towards the best practice guidance that we have seen recommended by the IAU CPS. And then want to start looking at reporting and evaluating progress towards reaching that metric. And again, then maintaining an ongoing collaboration between industry and science. So some of the key coordination requests to date have been focused on provision of telemetry, asking folks to do an analysis with the Laser Clearinghouse, and I'll just mention that in the next 2 slides quickly, working towards reducing their brightness to about 7th magnitude or fainter and choosing altitudes of 700 kilometers or lower. These we're definitely happy to start refining, and we already have a little bit, especially the brightness, that maybe 6.5 would be sufficient. But as we hear updates from you and the community, that'll be great to feed back to make sure that what we're requesting is the most up to date. It's great to hear all the work on orbital debris. We haven't made orbital debris mitigations a focus of our request because there's a lot of work by NASA and others on long-term sustainability and orbital debris mitigation. But I think hearing how important that is, we might start adding just some comments about how that can also support astronomy, that we actually have systems that are, capable of avoiding falling apart and collisions as much as possible. And then we'll continue to support NASA on that front as well. So just concluding really quickly, I wanted to mention the Laser Clearinghouse. You had heard a little over a year ago with NOAR Lab, we had sponsored a workshop at the Vandenberg Air Force Base on looking to mitigate the impact that the ground-based optical lasers having to shut off when satellites are passing. And this doesn't impact Rubin directly, but probably follow-up observations of Rubin transients folks might be really interested in. So the main update I wanted to share with you is since this study, we've actually funded a technical study by the Air Force Research Lab Satellite Assessment Center, who's looking in great detail at, we provided the details of all of the optical lasers, and we're going to get a report back in about 2 months that we hope will be the basis of some new policy recommendations to help lower the burden on astronomical sites for the deconfliction periods. So with that, I know I'm kind of getting close to finishing time. Meredith already mentioned a recent funded award we have via SwiftSat. So I wanted to just conclude with, if you have other research ideas, we don't currently have an open call for funding, but contact the Rubin Program Officer, or you're welcome to reach out to the Spectrum Management Office if you have some ideas. And we're happy to hear those, whether it leads to the development of a new funding opportunity or maybe an unsolicited opportunity, you're always welcome to reach out. If you have contributions to the UN COPUS meetings for the next 5 years, that's a place where I think the technical work being done will be really helpful. So reach out if you want to get involved there. And just wanted to highlight again that I think it's really important to hear what these studies are. What are the science impacts and the trade-offs? Because one decision or thing that we encourage might help one area of science and hurt another. So that's one area that we want to really think about, is what trade-offs we're making when we make different recommendations, and what the community thinks is the best kind of compromise in terms of what we're recommending and pushing in the coordination agreements with the satellite companies. So yeah, that is, I'll just end here so we have time for questions. But again, thanks for your time and your attention and letting me be here.
Thanks very much, Ashley. We already are beginning to see, as you pointed out, we're already beginning to see an uptake on the part of at least some operators of the need to mitigate their brightness. So this is the beginning of the Q&A session, but I think we should start with responses to the points that you brought up. Any questions in the room? Yes, sir.
I kind of wanted to ask because, you know, like you just mentioned, the idea of limiting magnitude is a great move. Is there any, do you see any likelihood of that becoming like mandated, especially when we see things like Blue Walker 3, which is glaringly bright?
I'm gonna let Ashley answer.
I'd say that's a really good question. And one of the questions that we get back from satellite operators is, what does a limiting magnitude mean? Is this going to be the maximum brightness that you observe over the whole sky? Is it an average? Is it a median? Is there some percentage of time that you can, especially when you're getting these kind of flares? So I think that's one thing that maybe is on astronomers first, to establish a baseline of what we mean by a certain brightness and how does and tie that into sort of the impact that it has on science. We're recommending this, you know, this is how you would make that measurement. This is what it means. This is what percentage of time you could exceed it in certain windows. And I think once we have that and it's tied to the science and it's very strong, then I could imagine eventually leading that into, you know, something that might become a stronger standard. But it's pretty hard to just establish a standard when we can't even provide, you know, really strong guidance yet on what that even means precisely.
Thanks. Any questions online? I've noticed that with regard to this question, the satellite operator community has begun to chip away at this definition of magnitude. Originally, it was how bright at any particular time can my satellite be? And we gave them a single number, 7th magnitude. And it became a little nuanced, and people were saying, well, you know, how about 6.5? Would you believe 6.3? And only at a certain time. Question here.
Ashley, thanks for all that information. You're talking a little bit about the radio and the infrared and the optical altogether, and we heard earlier satellites. So some satellites painting themselves black, and I remember hearing that makes the satellites, you know, hotter, and then actually just pushes a lot of the problem to the infrared. Can you talk about that? Is that still the plan for some companies to paint black?
Right. So SpaceX first tried, just as an experiment, to paint their solar array black, and of course it overheated and killed their transmitter transistor. So they knew that was probably going to happen, and it did. So they gave up on that. Then they had sunshades.
Yeah.
And that was great until they started interfering with their laser communication system, which had to go down to other satellites. And so now they have decided and they have implemented to coat the bottom side, the nadir pointing side of their satellite, with a mirror surface to reflect the sun off away from the Earth's surface to space. And that is the current generation of the satellites that are up there, and those are the ones we're dealing with right now that are appearing to be a little disturbingly bright for some reason. Don't understand why. And some of them are being seen at midnight. So who ordered that? Because that's in the Earth's shadow. That's in the shadow. So what's going on there? A lot of work to be done. Any questions online before? Go ahead. Yes. Here.
Of the light from cities can actually be reflected in satellite?
What was the question?
Earthshine.
So Earthshine is included in our calculation. It's in the calculation. It can't explain what we see. But you're right, it does come, it's a component, and we're writing a paper on this right now.
Satellites shining off of each other.
Yeah, so bounce, 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 bounce. It's a minor component. And then what they've done is to paint the obvious white cables black. That has helped a lot. But there are issues like the edges of solar panels and whatnot. But I emphasize only certain companies have begun to deal with this. Others have basically said forget it. We're just going to do what we're going to do. We don't care about astronomy. Question.
What about, I heard some companies are trying to do, turn the satellites onto a knife edge in the corner.
Yes, yes.
What's the status of that?
Yeah, so at least SpaceX has volunteered to temporarily, for a while, turn their satellite on a knife edge. Of course, they lose power by doing that because so okay. But generally speaking, that company and Kuiper, Amazon Kuiper, are entertaining the notion of somebody else said nuanced attitude. So when they're in a particularly bad orientation with respect to say our telescope, they'll change the orientation for a while, and they only lose a little bit of power that way. But that's not a general solution to the problem.
If I could jump in briefly on that point. I think that a lot of the questions here have been pointing at a really key take-home point, and that is that the satellite operators are constantly iterating and changing their designs, sometimes for their own purposes to, better sell whatever kind of connectivity they're offering, but also in response to what we and others are saying about how the satellites are appearing. And so if you're interested in this kind of like iterative observe satellites, see what they do at certain positions and locations, provide feedback to operators, kind of cycle and, maybe even publish papers along these lines, I would love to talk to you because we need more people to help with that kind of work at SatHub, and it's really timely and important.
Yeah. It's great to see this progress, but I just want to make a very brief mathematical point, purely math, nothing else, no politics. On the right-hand side of the equation, you have pretty much a constant, which is basically, in my experience, the timescale on which the United Nations moves. On the left-hand side of the equation, you have that exponential that you saw this morning. There's only one solution to that equation at only one time. So choose your time and your coefficient, but there's not a general solution. Is that happy note? Any other questions? Matt.
When this all sort of got going a couple years ago, there was some hope perhaps that the economics of the business model would limit the total number of satellites. But I note that Starlink is going to make $7 billion this year. They're aiming for 40% profit margin. They're not the only ones in the business. This is a business that seems to be growing as we're seeing exponentially. Are there any informed models now looking at the business side about how many satellites you think the world's actually going to support?
That's a good question, Pat. Basically to recap, there are tens of billions of investor dollars chasing this direct to cell, and companies are jumping on this. And some of them are new companies that basically build satellites, and they don't care. They just build satellites. Build me a satellite, and so that's an unhappy situation. Yeah, I think that we can negotiate with the companies that want to play ball. But another issue that Ashley didn't mention is that if I want to build a satellite constellation, and at least part of my company is not in the United States, I could go shopping around for permission to launch. And this has been done by various companies overseas. And so I don't have to go to the FCC. And so I get permission to launch all my satellites. I just have to turn the transmitter off above the US if I don't have an FCC. But I'm still reflecting sunlight over the US and Chile.
So could we wind up with really 500,000 satellites in the sky?
Yeah. The best guess is about 400,000. And so what will probably, I think the recording is still running, but I will go out on a limb. Well, okay, so the Department of Defense did an analysis of this issue a while ago, and part of the unclassified part of the analysis is now public. It was released by the NSF. Their conclusion was that as soon as you get above about 40,000 satellites in low Earth orbit, that's less than 600 kilometers, you have a 50%, increasingly 50% or greater probability of a collision runaway, sometimes called a Kessler syndrome, where a satellite collides with another satellite, which then the debris then destroys other satellites, and you have an exponential runaway. There's some chance that this is going to happen. A big chance, in my personal view. That would be bad for everybody concerned. So I could imagine somebody saying, okay, that's it, no more launches. That's a way of cutting off that mathematical equation that I mentioned.
Forcing that to be challenged.
That would be an interesting event. Any more questions? Solutions? Anybody? We need solutions. One of the things that was mentioned earlier is that we now need to segue beyond what's currently been done in the lab and in space. Must consider space as lab. It's a really interesting concept. Launch it and then fiddle and then destroy it, rather than go into the lab and do an experiment. Yeah, there's a lot of work to be done, but I think we need to segue away beyond what we now understand, and there's a lot that as we've heard today, that has been done in just the last year. We want to go the next step, and as a community, use this information, and it's a lot of rich information, data, in full forward simulations of our science case. Whether it be searching for near-Earth asteroids or looking at the late stage of the expansion of the universe, trying to ask what's going on here. They all are affected, all these adventures in science. And it's going to be a real adventure. And our hope is that particularly the younger generation that's going to inherit this wonderful data won't be hamstrung with trying to analyze data that's infected with all of these crazy things that are creating bad correlations or fake events, bogus galaxies. There are such things, bogus galaxies. They exist.
Got to take the tinfoil off.
You've got a solution, Ian?
No, it's going to be a problem that's going to.
It's going to be an interesting time. And it's a lot of computation to take your science case and do a full forward. It's a lot of computer simulation to be able to do that. But I think that's the next step.
Actually,
any more questions here? Otherwise, I think we're
actually I have one question based on that, which is,
yeah,
I can imagine that this is the kind of thing you have to Monte Carlo as well.
Yes,
it's a big
you have to Monte Carlo it. Yeah, you can't just do one simulation and say, okay, done. Yeah, you have to do many simulations and look at the distribution, talk likelihoods.
So people started thinking about supercomputer allocation requests.
People are beginning to think about that. Definitely. We've been using San Diego for a lot of those. And Irfan is here, way over there. We've written a paper on this even, so we're beginning to chip away at this. But I think it's me personally, this wonderful, delightful project is for the next generation, and that's the personally that's the exciting part. about it. Okay. Thanks, everybody. I think it's 12 now.